So within this presentation, I'll talk about our latest development in glass-based photonic circuits, and actually most of them over the past year have been undertaken and funded by the MASSTART project, as we'll see. It's always nice to start with a little bit of corporate background. So we are an SME based in Grenoble, not so far from Leti, as Quentin mentioned. The company was initially incorporated to make actually PLC splitters and other kind of glass-based components for passive optical networks. But after the dot-com crash in the early 2000s, it acquired the Q-switch microchip laser line from JDSU, and since then we share our staff and I would say revenue in between two activities. So these lasers, which have nothing to do with telecom, and the PLC manufacturing, so glass-based integrated photonics. So right from the beginning, Teem Photonics leverage a specific manufacturing process to make these PLC circuits, which is called ion exchange, or IONEX as a brand name. So it's once again a specific process to obtain these glass circuits. So we start from a bulk silica wafers. We have a few steps in the clean room to pattern the wafer. So with an aluminum mask and 400 nanometer photolithography, we open the mask and then we step out of the clean room and we perform the ion exchange per se. We'll see on the next slide. It's really about dipping the wafers in a hot solution and locally doping the substrate where you want your waveguides to be. After that, we have some in-house equipment to perform dicing, pigtailing, and packaging of standalone chips, and also, as we'll see in MASSTART, some tests for a hybrid integration with silicon photonics or so. So we have a little bit of a side space, I would say, in MASSTART, because of course glass is mostly interesting for passive functions, but there are nice properties for that you can leverage, like a wide transparency band. For the topic of today, so of course it's we can cover any transmission, like telecom transmission window, with a low propagation loss of about 0.1 dB per centimeter. Our waveguides, their polarization maintaining, show low PDL, low birefringence, and low temperature dependence. We've just characterized it to be like really a fraction of effective index variation per Kelvin. So that's especially interesting for uncooled systems, for instance. Also for coherent systems and so on, when it comes to polarization. And at the same time, we have a few specifics, like our at least in the reference frame of glass, our circuits are quite compact, so that we can cram quite a lot of function on a given footprint, and we have a good coupling loss with optical fibers. We'll see how we can leverage that. So here I say a few more words about the physics. Won't spend too long on that, but essentially it's because ion exchange is a well-documented process, a pretty old and well-proven one. But yeah, what I can say is that we end up with our standard process with gradient index distribution and relatively confined waveguides of 4 by 3 microns in MFD in the telecom bands. We also have the possibilities to make tapers at the facets. So they are not inverse tapers like what you can see in nitride or indium phosphide, but actual tapers that expand the mode towards 10 microns to obtain a very nice and low loss coupling with the optical fibers. So I would say beyond that, we can definitely use this gradient index waveguides that can be a little like sometimes a little scary to people that are used to, I would say, step index platforms like PLC or silicon photonics. But I can assure that such gradient index waveguides can be, I would say, turned into optical function in a very robust ways. And actually within the MASSTART project, we've put a lot of effort to standardize our, I would say, our design process into modern, what you can find in modern integrated photonics. So we've developed a PDK with a lot of support from Bright Photonics, actually. So now It's all implemented with their NASCAR design suite, and it's continuously updated with passive functions such as splitter, couplers, multiplexers. I'll say more words about it. Can be like slab interferometers. We can make waveguide crossing, Bragg ratings. We have several ways to implement it. And we usually take on customer projects right from the design, so turn the concept into a GDS, down to manufacturing. But now that we have a PDK, it must be noted that we can also resort to a design house like Bright Photonics, for instance, to help us with the design. And I would say as latest novelties, we're undertaking projects to add some actives in our PDK, so thermo-optic phase shifters. I think Quentin summarized well the advantages of silicon nitride. I would say with glass, you go one step further when it comes to stability and environment insensitivity. And we're also working on a few functions that act on polarization, starting with filters, for instance, to eliminate the TM or TE modes when only one mode has to be processed on chip. So yes, because we started with the manufacturing of PON components, we've kept a good expertise in fiber to chip assembly. So we'll see that for the interposers that we make available to the MASSTART project, it's useful, but it can be useful for any PLC project that we put a strong emphasis on making them lab ready when we deliver custom components. So now going to the actual topic of today. So our initial role within MASSTART was to provide glass-based interposers to ease the coupling in between the main hardware, I would say, so the silicon photonic modulators and the 3.5 lasers that Sofiane just described. And for this, we based our work on what we call the existing WAF solution. WAF stands for waveguide array to fiber transposers. And so these interposers, they've been devised to address the three type of couplings that you will encounter in integrated photonics, with the two first one, edge coupling and top coupling, being the most common ones. I think Quentin already went over the pros and cons of each coupling type, like when you use edge coupling through the phase sets, it's pretty nice because it's relatively low loss. So we mentioned that we've demonstrated a coupling loss below 1 dB with the chips from Leti. It's WDM compatible, which is especially interesting within MASSTART, where we target WDM schemes in the O band. It's TE and TM compatible. But it poses some wafer level incompatibilities, as once again Quentin described, starting from actually the wafer level testing and component testing, and the alignment accuracy is relatively tight. Top coupling results to grading couplers, so it's more alignment tolerance, but and it's wafer level compatible when it comes to testing. But the grading couplers are more lossy, and they're usually a little bit WDM limited. And we'll see that evanescent coupling is more advanced, but aims at combining the advantages of both. What we offer for edge coupling is called the EC-WAF. So it's actually a small PLC circuit that has to come in butt coupling, like butt coupled with the PIC and on one side and with the fiber array on the other side. So it actually shows two functions. One is shrinking the mode field diameter from 10 micron on the fiber side down to 3 micron on the PIC side to adapt the MFD adiabatically. And on top of that, it can shrink the pitch to down to 20 micron, which when one has to deal with a large number of channels, can be very advantageous because it relaxes the alignment constraints. If you have a large number of optical IOs with a standard pitch of say 250 microns, you can expect a hard time finding the right alignment. Whereas if you go to 20 microns, let's say, it's going to be much looser. So it's more relevant for switching, which was the case of the packaged chip picture shown here. But yeah, that's still well within the, I would say, data center interconnect topic here. So yeah, EC-WAFT is made for edge coupling, and it's an all but coupling configuration in this case, unlike, for instance, micro lenses or lens fibers. The tap coupling WAFT was mentioned by Quentin for wafer level testing of edge coupled peaks. So it's just a reminder here, bottom right. But essentially, this PLC, so in blue here again, was devised to offer a low profile coupling with grading coupler. So instead of having a bulging fiber array stuck on your peak, so a high thickness subsystem, I would say, here, thanks to an angle polishing at the tip of our PLC, we can deflect the guided beam down towards the grading coupler. And we've shown in several projects that this performs exactly the same as a fiber array, but of course in a low thickness configuration, which is usually pretty nice for photonic packaging. So the first configuration I've talked about is called Evanescent Coupling. So EV-WAFT actually stands for Evanescent. And that was devised initially by one of our customers who wanted the advantages of edge coupling, so WDM and I would say polarization diversity handling, as well as some passive alignment capability. And he's come up with this idea where the light is directly coupled through the evanescent field from our interposer down to the silicon nitride tapers. It was, in their case, it was leveraging the silicon nitride layer that Quentin talked about. And this is achieved by etching away the cladding actually on the peak. So it poses a little bit of constraint on the peak processing. But if you're able to remove the cladding and the back end of line over a few millimeters on the peak, then we can make an interposer with a surface waveguide that allows the two waveguide layers to come in very close contact, just a few microns away. And in this case, light is really transferred as is in a directional coupler. So ST at the time had shown that they can achieve a pretty low loss of 1.5 dB from the optical fiber to the SIN layer, a low PDL, and a certain alignment tolerance with respect to tilts and the glue layer thickness, for instance. Yeah, so I would say that was for silicon photonics packaging, but MASSTART has recently given us the opportunity to work on our actual PLC capabilities. And we've undertaken joint AWG developments with Bright Photonics in the O-band and C-band. And I would say it's a work in progress, but we've already shown that we have a low polarization and low thermal sensitivity. So once again, it's the similar pros that you may imagine with SIN, but going again one step further. And yeah, we're working on AWGs for DWDM from 50 gigahertz spacing up to a CWDM, mostly for telecom and datacom. So they are relatively compact thanks to our confined waveguide on glass. And yeah, we're really working at improving like the crosstalk and insertion loss. So once again, it's a work in progress, but the results are very encouraging. On top of that, it's worth mentioning that we're also working on very high channel density AWGs with very fine spacing. So I cannot say too much about it because it's we're at the early stage of the project, but it's the same concept, and we are really determined to prove that once again this gradient index platform of ours is suitable for high accuracy components like these. Well, and the idea of developing these building blocks on glass, as I said, because it's mostly passive, the idea is really to hybridize them with other platforms, starting, of course, with silicon photonics and indium phosphide lasers on MASSTART. So, for instance, AWGs, they could be combined with the silicon chips, with silicon photonics modulators, but that could also be lithium niobates on insulator, for instance. To make temperature robust and fabrication tolerant systems. For instance, you can imagine of having a device that are a little bit more sensitive to yield, like AWGs on glass, which is a cheap platform, and high-speed modulators on active platforms. Another project we've encountered recently was to, for instance, split the power per I/O that is injected on the peaks, thanks to our WAFT in LiDAR or photonic computing, where there is quite a lot of power needed on chip, but that the interfaces cannot necessarily take up all this power on one I/O only. So it can be interesting to split it on glass before injecting it all on silicon. And we've shown on other side projects, so it's not directly MASSTART, but that glass can hybridize well with, for instance, bulk lithium niobates or even glass micro benches made at Fraunhofer IZM on a side project. So it's a very flexible platform actually. A few last words. So about our erbium doped platform. So back in I would say 15 years ago, Teem was commercializing these erbium doped waveguide amplifiers, actually that were a little bit limited in saturated power and overall gain to compete with very efficient and compact fiber amplifiers, even at the time. But this technology is still, I would say, live and available on our side for, once again, hybridization with silicon photonics, for instance. It can be envisioned in the C-band to compensate for some loss, let's say, on silicon, with amplifying interposers or similar schemes. So yeah, with that, I'd like to thank you for your attention, and yeah, ready to take on questions if there's any.
Thank you very much, Adrien. There are actually already 2 questions from the chat, 3 now. But in the interest of time, I would ask you to also reply to them in the chat, and we move on to the next presentation.